we talked a lot about normal series, alternating series, p-series, telescoping series, geometric series, and so on, and how to determine if they converged or diverged. Well, now we've been dealing with what are called power series. Now you can see kind of the definition of power series right here. AN can represent anything. So the point is that somewhere in the power series you have x to the n, and it can be x to the 2n or x to the n plus 1, or it can be variations of that, but it's got to be something close to that. Okay, now it can have anything else with it, but it contains x to the n. So if you think about it, the value of x is going to affect whether or not the power series converges. So one thing we have to do with power series is determine, well, when does it converge? In other words, under what values of x will this converge? And I think this example at the bottom is one of the easiest to explain how that would affect it. So just consider if I told you that x was equal to 3. Well, if x is equal to 3, then this is a geometric series, and since the r, that's the number in the parentheses, is less than 1, it's clearly going to converge. But if I told you that x was -5, this would still be a geometric series, but it would not be converging because the r is less than -1. Remember, the absolute value of the r, again that's the number in parentheses, has to be less than 1. So the first one, when x is 3, converges. The second one, when x is -5, diverges. So we've got that going on both ways. So we have to know, okay, well, what x values can we plug in to make it converge? So for this one, if you're clever, you can probably just look at it and tell. We know that for a geometric series to converge, the r has to be less than 1. So, and again, that's the absolute value of r has to be less than 1. So x can be anywhere between -4 and +4. Now I cannot include the 4's because it cannot equal 1 for the geometric series. That also diverges. So you could also write the interval this way, -4 to 4. So that would be what's called the interval of convergence. Now there's 3 possibilities when it comes to the interval of convergence. First, it's possible that it will converge only at its center. Now if you remember when we were talking more about geometric power series, the center is the number that if you plug it in for x, makes the whole series 0. So for this previous example, it would just be 0. If you plug in 0 for x, it turns everything to 0. You'll always converge at the center, no matter what, because you can add up 0 all you want, and it's just going to be 0. So it's possible that that is the only place it will converge. It converges only at its center. The second possibility is that it would converge only around an interval, only on an interval around the center. That would be the case in this first example as well, because we would be centered at 0, but we converge on an interval around that, from -4 to +4. And notice 0 is the center of that interval as well, and that's not a coincidence. That's how it should be. So in other words, basically starting at your center, 0, you can go up 4 or down 4 and still be converging for this particular series. Now the third possibility is that it converges for every value of x. There are some power series where any x you plug in, it's still going to converge. So that's the third possibility. Okay, so we're going to start by talking about the radius of convergence. Okay, just the radius of convergence. The radius means how far can you go from your center and still converge. And the way we can determine that is with the ratio test, which we've done before. So let's perform the ratio test on this power series. We do the limit as n approaches infinity. We put the original on the bottom. And on top, we add 1 to every n. So we make it x to the n plus 1, and we make it n plus 1 factorial. Well, that can be rewritten as x to the n plus 1 times n plus 1 times n factorial over x to the n times n factorial. So let's look at what will cancel out. N factorial will cancel, and all the x's will cancel out except for one of them on top. So we end up with just x times n plus 1. Okay, now we're doing the limit as n approaches infinity. So for the sake of the limit, you treat x basically just like a coefficient, because x isn't what we're sending out to infinity. N is. So n is what's going to infinity. Well, since we just have n plus 1, as n approaches infinity, this is going to approach infinity. Okay, now here's where you have to be a little careful. The ratio test says if your limit is greater than 1, then you diverge. So, because we got a limit of infinity, that means the radius of convergence is 0. Now that may feel backwards, but again, if you'll think about what the ratio test says, it should make sense. The ratio test says if your limit is greater than 1, then you diverge. So the fact that we got the limit to be infinity tells us that this thing is going to diverge everywhere, except of course at its center, because we know it always converges there. So the fact that it diverges everywhere tells me that it converges nowhere, again, except the center. So its radius of convergence would be 0, because you can't leave the center and converge. The center is the only place it will converge, because everywhere else it will diverge. So the radius of convergence would be 0. Okay, next up, find the radius of convergence for the series that we did earlier. So I'll show you how to work this one out. We do the limit as n approaches infinity. We put the original on the bottom, and on top we add 1 to the n. Okay, well that's going to cancel out everything but a single x over 4. Now remember I said just a second ago that we're going to be treating x like a coefficient. Well, that means if we're doing the limit as n approaches infinity of x over 4, the answer is just going to be x over 4, because there's no n going to infinity. So we just have a constant. We just treat it like a constant, x over 4. Okay, but we're not quite done yet. This is our limit. Our limit is the absolute value of x over 4, but we want to know where it converges. So you have to think back to the rule for the ratio test. The ratio test says if your limit is less than 1, then you converge. So let's rewrite this a little bit. We can rewrite this as absolute value of x over absolute value of 4. Absolute value of 4 is just 4. So I can have it written like that. Now if, okay, now this is just saying if the absolute value of x over 4 is less than 1, we converge. So I'm not stating that this is always true. I'm merely saying that when this is true, that's when we converge. Because when our limit is less than 1, we converge. So now, if I multiply both sides by 4 to simplify this, I get the absolute value of x is less than 4. And it turns out this is my radius. So the radius of convergence is 4. Okay, again, when I set it up less than 1, I'm not stating that's always true. I'm merely wanting to find out when that is true. So the limit is less than 1 as long as the absolute value of x is less than 4. So that tells us our radius of convergence is 4. Again, what that tells us is that based on our center, which in this case would be 0, we can go up to 4 or down to negative 4 and still be in a range that's converging. Now, whether it converges or diverges at negative 4 and positive 4 at those actual values, we'll get to in a second. But the point is you can at least go all the way up to those, if not equal those, and still converge. You can almost think about it just like a circle. Okay, so you can go 4 this way or 4 this way from your center, and that's your radius of convergence. Okay, let's do another one. Find the radius of convergence for 3 times x minus 2 to the n. So we do the limit as n approaches infinity, because the way to solve a problem where you're looking for the radius of convergence is using the ratio test. We put the original on the bottom, and on top we add 1 to the n. So that means the 3 cancels out, and all of the x minus 2's cancel out except for 1, so it gives me x minus 2. Okay, now there's nothing I can do to simplify this. There's no way I can pull that negative 2 out because I have to subtract before I do the absolute value, so I have to just leave that as it is. And what the ratio test rule says is that if my limit is less than 1, so this is my limit, x minus 2, because remember x is just a constant in this case, because it's in we're doing the limit of, and it's gone. If the absolute value of x minus 2 is less than 1, then we'll converge. Since there's no other simplifying, 1 is your radius of convergence. Okay, one more for the radius of convergence. We have the limit as n approaches infinity, and we put the original on the bottom. And on top, we add 1 to all the ends. Now, you actually have to do it like this, which is going to turn out to give you 2n plus 2 in both of those cases. The reason again for that is whatever was happening to n, you have to do to n plus 1. So if n was being doubled, n plus 1 has to be doubled. So we end up with x to the 2n plus 2 over 2n plus 2 factorial. Notice I didn't include the negative 1 to the n. That's because of our absolute value signs. All negative 1 to the n does is alternate between negative 1 and positive 1. And since we've got the absolute value signs, it's just going to make it positive 1 all the time, so there's no reason to write it. Okay, so we have a fraction over fraction, so we'll need to multiply by the reciprocal. And I'm going to rewrite this factorial as 2n factorial times 2n plus 1 times 2n plus 2. And then I have to flip the bottom fraction, and I get this. Now I should have absolute value signs here. The 2n factorials cancel, and all of my x's will cancel except for 2 of them. Okay, there's 2 more on top than there are on the bottom, so I'll have 2 left over. So that leaves me with the limit as n approaches infinity of x squared over 2n plus 1, 2n plus 2. Remember, x is just treated as a coefficient. So x squared on top is just like having a 3 on top or a 4 on top. It's just a number. Now as n goes to infinity, that means the bottom is going to infinity, which means our limit will be 0. Okay? So think again carefully about the rule for the ratio test. The ratio test says if your limit is less than 1, then you converge. Okay, so in this particular problem, it doesn't matter what x is. I could pick any x I want, and the limit is still going to be 0. So that means we always converge. 0 is always less than 1, so we always converge. And if we always converge, then our radius of convergence would be infinity. Okay, so I know again that may seem backwards, but if you think carefully about what the ratio test says and its rules, it should make sense. If our limit is less than 1, in this case 0, that means we converge, and we converge everywhere. It doesn't matter what x is, we just always converge. And if we always converge, then our radius of convergence would be infinity. So on 2 examples before this, this one and this one, you see x was part of our limit. So when we took the limit, x still showed up. So it depended a little bit on x how our radius turned out. Whereas in our very first example here, the limit was just infinity, x was gone. And in our last example here, the limit was 0, x was gone. So in that case, it didn't matter what x was. It either always converged, in this case that's up right now, or in that first example, always diverged. Now that we know how to find the radius, we're going to move on and talk about how to find the interval of convergence. But I'm going to do that in the separate videos, so make sure you go to part 2 for that.